Right, we are looking at the area under a curve or under a graph using the trapezoidal rule or using rectangles. And then the other method will be to use integration. Okay, so if you're asking a question to find the area under a curve, it is also the equivalent of being asked to find the distance traveled in that time interval. So, the interval on the x-axis over 0 to, whatever value this would be up here. Or if you look at this graph from A to B. So that's just something to note. Questions that involve distance, speed and time, I suppose, can also be reflected on a graph. So finding the area under the graph can also represent the distance that was traveled in that time frame. Okay, so there's two ways that we're going to look at it. One is an approximating method, which will be this method here, where you can draw in rectangular blocks. Each will have an equal width, and you could get the area of each one of those blocks and add it together, and you'd get an approximate area under that curve from 0 up to whatever this value here would be. And that's only going to be an approximation because, as you can see under the curve, there's little white regions that haven't been accounted for. So that's why it's only going to be an estimate. Over here then, you'd use the integration method. So if I get the area under this curve, f of x, so obviously it's going to be the integral of whatever the f of x function is, from this interval, the lower interval would be a, to the upper interval of b. And that would give me the exact, accurate answer for the area under that curve between those two values. Right, if we look at the following example, it says to approximate the area under the following curve or under the following graph, which is a quadratic, and the x-axis over a certain interval. So the interval goes from 0 to 3 on the x-axis. So there's 3 units of width there. By fitting in 4 rectangles of equal area. So each of them will have an equal width across the x-axis. Okay, so 4 rectangles of equal area. Sorry, that shouldn't say equal area, that should say equal width under the graph, and then adding your answers together. Okay, so I'll just fix that word. Right, okay, so the question said approximate. So we're going to use the estimated approach, which is drawing in the rectangular blocks, which is what they said. Okay, so draw in 4 rectangles. So if I was to draw in 4 rectangles, and each of those rectangles have to have an equal width, well, you've got 3 units of an interval, but I want to put in 4 blocks. So the width of each block would have to be 3 units divided by 4 blocks. So you get 3/4, or 0.7 as a decimal. So that means if I went to 0 on the x-axis and then I go to 3/4, which would roughly be there, that would be my first block. If you add on another 3/4, that would bring you to 6/4, which would roughly be there. If you add on another 3/4 onto that, that would bring you to 9/4, which would be roughly there. And then obviously if you add on another 3/4 onto that, it would bring you to 12/4, which is technically 3. I would then draw in each of my rectangular blocks. You could use a ruler, obviously, to do this. There's my 4 blocks. They each have the same width of 3/4. And as you can see, it's only going to give me an approximate answer for the area because look at this region here. Like, that's not being accounted for, that's not being accounted for, and that's not being accounted for. And that little small bit down here also would not be accounted for. So I'm only going to get an estimate. And my estimate is obviously going to underestimate the true area under that curve from 0 up to 3 units. So obviously if you ask yourself, well, how would I get the area of a rectangle? It's length by width. So we know the width is 3/4, so all I have to do is get the length, or well, you can call it a height in this instance. So I need to get the height of each block. Well, the first height is 1. And if you didn't copy that from the graph, if you sub 0x into the function x squared plus 1, you will get back 1 for the first height of that block. To get the next height of this block, you're going to have to sub in 3/4 because that's where it is on the x-axis. So if you sub 3/4 into that function, you'll get back your next height. Okay. Then here, this is 6/4, otherwise known as 3/2. Simplify the fraction. So if you sub 3/2 into that function, you'll get back the next height. Okay, which is that one. Then 6/4, add on another 3/4 onto that, and it's bringing us to 9/4 here. If you sub 9/4 into that function, okay, you will get back this corresponding height. You will then have all of the heights of each of the blocks, or you can call it the length of each block, and you're just going to multiply each of the lengths by the width of 3/4. And that will give you the area of each block, and then you just add your areas together. Okay, so here's the workings done. each of the x values on the x-axis. I've just written them in here, right? It was 3/4, then it was 3/2, and then it was 9/4. Okay, and when we subbed each of those values into the function for height, we got back our corresponding lengths of the block, okay, or the heights of each block. So then the area formula is going to be length multiplied by width. So you can see here, area is going to equal the first block, it's 3/4 multiplied by a height of 1. The next block is 3/4 multiplied by a height of 1.5625. The next block is 3/4 multiplied by 3.25. And the last block is 3/4 multiplied by 6.0625, which gives me an estimate for the area under the curve over the interval from 0 to 3 on the x-axis of 8.90625. Area is units squared. And remember, that is only an approximate answer because of the white space that we haven't accounted for. The only way to improve that estimate would be if you actually used more than 4 blocks, like if you doubled it and you had 8 blocks, or if you doubled that again and you had 16 blocks, because that would end up minimizing the amount of white free space that isn't being accounted for. Now, it would still only be an estimate, but it would be a better estimate than what we've gotten here. Right, back to part 2. It said approximate the area under the graph, so it's the same graph, and the x-axis over the same interval, 0 to 3, by fitting in 8 rectangles this time of equal, again, it's not equal area, it's equal width, under the graph, and then add each of them together. And explain why this approximation is better than the answer that you got in part 1. So we're now going to just draw in 8 blocks and we have to do all the same work again. Okay, so here's my diagram. So now I have to get all the new values on the x-axis. So remember, they're all of equal width. So I still have to draw in 8 blocks over a 3-unit space. So it's going to be 3 units divided by 8 blocks, which is just 3/8, or 0.375. So each of the widths of each block is 0.375 units, or leave it in fraction format, 3/8. Then I'm going to figure out what each of the heights are. So obviously the first height is arrived at by subbing in 0 into your function, okay, and you'll get back 1. Then the next height would be at 3/8. Add on another 3/8 onto that, it'll bring you to 6/8. Add on another 3/8 onto that, it'll bring you to 9/8. Add on another 3/8 and you'll get 12/8, and so on and so forth until you get up as far as 3, because that would be 24/8. So I now have all of the values on the x-axis in order to be able to sub into the function to get back the corresponding heights of each of the blocks. So that's what I'm going to do next, sub them all in. Okay, so when you sub in all of your x values, you'll get back all of your corresponding heights of each of the blocks. And remember, the formula for the area of a rectangle is length by width. So it's going to be, all the widths are the same, they're all 0.375 units. So it's the width multiplied by the height of the first block, plus the width multiplied by the height of the second block, plus the width multiplied by the height of the third block, and so on. So all I've done here is I've actually just factored out 0.375 and then multiplied that by all of the heights, because it would be the same thing as if you did it individually. That gives me an approximate area of 10.38 units squared for area. And that's a larger value than what we got the first time when we only used 4 rectangular blocks. Okay, so it is giving us a better estimate, and the reason why is because you are minimizing the amount of space under the curve that hasn't been accounted for. So by increasing the number of rectangles, you have reduced the area that would have not been used or not been calculated. Now, the accurate answer would be arrived at by using integration instead. So it's the same graph, find the area under that curve from an interval of 0 up to 3. So all we have to do is integrate that quadratic function over the interval from a lower interval of 0 up to 3. So it's just the definite integral is what we're doing here. And again, I should have a dx there. So we're integrating that function with respect to x. All right. So when I integrate x squared, I'm going to get back x cubed divided by 3. And when you integrate 1 with respect to x, you'll get back 1x. I'm then subbing in my upper interval of 3 and my lower interval of 0, and I'm subtracting it. So if you sub 3 into that function, this is what you're getting back, which tidies up to be 12. And when you sub 0 into that function, you get back 0. So it's going to be upper take away lower, 12 take away 0, which is 12 units squared for area. That's the accurate answer for the area under that curve from 0 up to 3. So you can see it is similar to the answers we got for our approximations. So our approximation here, when we had the 8 rectangles, was 10.38. When we only had the 4 rectangles, it was 8.9. So obviously we are getting the accurate answer of 12, but it's not too far away from what the 2 approximate answers were.